So the way it works is that for each pixel, we need to calculate exactly what is the signal component and what is the noise component. So to do that, we take each camera model in the lab, and with all the illuminations from completely dark to completely bright, we illuminate all of the pixels with all the setting combinations, and then from that we extract a calibration file, and that calibration file will tell for every pixel on the camera what is the noise and signal components are through an equation. And then once that is done, what Rawsie does is that it, like, you could see this as denoising, so it removes the noise at that single pixel level, but it only removes the noise which is below the actual noise level. So it's invisible because because the noise is anyway random, and anyway the dominant part of the noise is even preserved. So it's a kind of like invisible noise that that is removed, and this then allows the lossless part of Rawsie to compress the image a lot better. So the result is an image that looks exactly the same with this little added noise that is equivalent to ISO, as we said before, but which has a codec which is more inspired from the lossless codecs than from the lossy ones. And so this means that all the fine detail is still preserved, and that the actual information part is still there in the final file. So yes, so the trick is to get Rawsie to be aware of what is noise and what is signal. This is something that, like, maybe 10 years ago, it wouldn't have been possible, because the sensors were still working in the very classical regime, which means that I could have a certain number, and I wouldn't know whether maybe with some clever algorithm in Photoshop, I can recover some signal from that number. Whereas as sensors have become better, what they do is that they kind of zoom in. As they become more sensitive, they kind of zoom in on this kind of quantum regime and quantum noise that you naturally have in the light. And so what that means, and as well as they become, as their efficiency goes, to 90%, 95%, and the noise goes to basically zero, they become a lot more similar. So what it means is that we can really start from theory, of quantum theory, saying, well, this is the actual minimum amount of noise that you would have in that signal. And to test it, what we do in the lab is that we just inject a specific signal, so we know how many photons we've got, we send those on the sensor, and then we can whatever we measure, we can subtract the number of signals, the exact signals that we've put in, and we know that the rest is noise because we know what the original signal was. So this you can only do in the lab. So if you have just a picture, you wouldn't be able to know what signal and noise is, but if you've put the signal in there yourself, then you can distinguish what signal and noise, the signal and noise components. And because the sensors are so repeatable and so homogeneous, and so this is thanks to the sensor manufacturers that have done a great job, it means that once you characterize one camera, that calibration applies to all the cameras from that model. And of course you have to do so under all the different conditions that the camera may be in, so all the different setting combinations. So this is also why sometimes some setting combinations might not work. For example, very long exposure times or very high ISOs are very hard for us to work with in the lab because they're too slow, and so sometimes those images will not compress with Rawsie. But yes, we haven't really come across many people using those, extreme settings.